Okay. So today we're going to talk about operational amplifiers, op amps. These are little chips that amplify signals. We can use these chips in many different types of circuits to create different kinds of amplifiers. And we'll talk a little bit about that today. First, we're going to do a review of capacitor and inductor filters. Okay? And we'll go on and talk a little bit about the lecture. We'll talk about what op amps are, why we care, a little bit about how they work. What we'll see is that there are two golden rules for op amps. And if you can remember these two golden rules, then you can analyze and understand just about any type of op amp circuit that is out there. Okay? So we'll go over what those two golden rules are and how we use them. And then we will use those two rules to analyze a couple of op amp circuits. We'll analyze something called an inverting amplifier, and then we'll do another one called a non-inverting amplifier. Okay? So we'll look at both of these and we'll see how the golden rules can help us understand these two types of amplifiers. Okay? These are only a couple of the many circuits that you can build with op amps. If you go on and you do ET322, which is the next class in this series, we'll talk about some other types of amplifier circuits that you can build with op amps. But these are the two that we're going to discuss here in 302. Okay? After we analyze them with the golden rules, we'll see that there are some shortcut formulas that can help you understand the, what's happening with these circuits and do some calculations more quickly. But if you can't remember the shortcut formulas, you can always fall back to the two golden rules and they'll always work for you. Okay? Then finally we're going to go on to a lab preview. Today we're going to skip the multisim part that is in your lab book. That was sort of a long lab, and the multisim was interesting, but really the hands-on part I think is the most important. So that's what we're going to do. We're going to go straight to the hands-on section and build a real circuit using an op amp chip. So we're actually going to build an inverting amplifier, and then we're going to build a non-inverting amplifier. We're going to look at the input and output from both of those circuits. Okay? So do you guys have any questions before we get started?
So you're saying that you skip part 1A, 1B, 2A, 2B, and go directly to 3A?
3A is where we're going to start. Yep. Mm-hmm. Other questions? All right. So let's do a quick review of capacitor and inductor filters. So 2 lectures ago, we talked a little bit about RC circuits and how we could use them for timing applications, right? We said that we had a capacitor up here and a resistor down there. That was a simple RC circuit. And we could look at the input and the output from this circuit. And when we put a step change on the input voltage, the capacitor would charge up slowly, right? The capacitor acts sort of like a rain barrel that gets filled up. And the resistor was like the hose that we use to fill that barrel. So a bigger capacitor is like a bigger barrel, it takes longer to fill up. Smaller capacitor is like a smaller barrel, it fills up more quickly. And similarly, the capacitor or the resistor is like the hose, so a bigger hose will fill the barrel more quickly, a smaller hose will fill the barrel more slowly. So the resistor and the capacitor both have a part in determining how long it takes for the capacitor to charge up. And we can use the capacitor charge time to figure out, or to trigger certain events. And by setting this capacitor charge time to what we want, we can determine how long a delay we want this circuit to give us. Okay? So this circuit provides a timing function. That's what we saw 2 lectures ago. And then last lecture, we looked at the same circuit and said we could use it for other things as well. We said in particular we could use it as a filter. Now filters, in general, allow certain things to pass through and block out other things. So what were we filtering with this electronic circuit here? What's frequencies, that's right. So we talked about several kinds of filters, and each filter would allow certain frequencies through, and it would block or absorb other frequencies, right? Now with this kind of filter here, we have the capacitor up on the top, and we said that the capacitor allows high frequencies through, and it blocks out low frequencies. So what type of filter was this? High-pass filter, that's right. We call it a high-pass filter because it allows high frequencies to pass through, and it blocks out low frequencies, right? We said we could build a high-pass filter with an inductor as well. But in order to do that, we had to swap the places of the resistor and the other component. So now the resistor is up on top, and the inductor is on the side. So in this case, the inductor is sort of the opposite of the capacitor, right? The capacitor allows high frequencies to go through. The inductor blocks high frequencies. The capacitor blocks out low frequencies while the inductor passes the low frequencies through. So the capacitors and the inductors do opposite things. When we put the inductor down here on the side, like we said, the inductor allows low frequencies to go through. So the low frequencies can go down to ground here. The inductor blocks the high frequencies, so they don't go to ground, they go to the output instead. So again, the high frequencies go through to the output, and the low frequencies are blocked out or absorbed. So this is another example of a high-pass filter, right? Okay, and then finally we said we could build a high-pass filter that included both a capacitor and an inductor. So we could have a capacitor up here and an inductor down here, and that would allow us to have an even better filter. It would allow, it would cut off the low frequencies more effectively. Right? Any questions about that? Okay, so we said that we used a particular type of graph when we analyzed the performance of these circuits. So we would plot the ratio of output divided by input, and we would match that as a function of frequency. So what we said was that this was a high-pass filter. These are all high-pass filters. So at high frequencies, the output is essentially the same as the input. So out over in has a value of about 1, right? Then at some point, the filter starts to attenuate the output frequencies. So the output gets smaller, and the ratio of output over input gets very, very small. Okay? So we say that this filter passes these high frequencies, blocks out or attenuates these low frequencies. And there's this one particular frequency right in the middle where we say this is sort of the in-between point, the spot where we between the frequencies that we pass and the frequencies that we attenuate. So what did we call this frequency right here? What's that?
Cutoff frequency.
The cutoff frequency, that's right. So for a high-pass filter, we say that frequencies above the cutoff frequency go through, and signals below the cutoff frequency get absorbed or attenuated. Okay? And right at the cutoff frequency, this ratio of output over input was at a very specific value. Do you remember what the value was there? Yeah, 70.7%. Okay? So this is the frequency response graph for a high-pass filter. Okay? Any questions about that? Okay, so we said that we could use capacitors and resistors to make low-pass filters as well. What did we have to change in this circuit in order to change it into a low-pass filter? Yeah, we had to swap the positions, exactly. So for a low-pass filter, we had the resistor up here and the capacitor on the side. Now, since the capacitor allows the high frequencies to go through it, in this case the high frequencies are going to the ground and the low frequencies are going through the output. Okay? So we could do a similar thing with an inductor. In that case, the inductor would be up here and the resistor would be on the side. That would be a low-pass filter with an inductor. And we could do it with a capacitor and an inductor. In that case, we would swap the positions of the two components in order to make a low-pass filter. Okay? So, any questions about that? Okay. So, that was a quick review of capacitors and inductors and RC filters and LC filters. If we use an inductor and a capacitor, we call that an LC filter. Okay. So, any questions about that? All right. Then let's move on and talk a little bit about the main topic today, which is the op amps. Okay? So first of all, let's talk about what is an op amp. An op amp is a little chip that amplifies signals. That's the simplest definition of it. Okay, so this is a particular type of chip that amplifies signals, and we can actually use it in many different ways. It's very versatile. So we can build a lot of different amplifier circuits with it, like I mentioned at the beginning of the lecture. We're going to look at two today. We're going to look at the inverting amplifier and the non-inverting amplifier, and we choose which type of amplifier we're building by the way that we arrange the resistors around the chip. Okay? So op amps are very common since they're very versatile and they're fairly inexpensive. You guys have already seen them earlier this year when we built our fiber optic transmitters. The heart of that transmitter was the op amp, and that amplified the signal that was coming from your voice and made it big enough that it could power or modulate an LED, right? So remember back when we were talking about that, we looked at the resistors around that op amp, and we said that they caused the amplifier to have a gain of 10, meaning that the output was 10 times bigger than the input. And at that time we said, well, we're not really going to talk very much about it, but we'll come back later and see why that is. Well, that's what we're doing today. We're going to come back and we're going to talk about the 2 golden rules, and hopefully those will help us to understand how we get a gain of 10 or another gain that we want. Okay? So we care about these because they are inexpensive and there are many different types of circuits that you can build with them. So they're very useful things to have. A lot of people use them in their electronic design, so it's important to understand how they work when you're analyzing somebody else's design. And also, they're very useful tools to have in your toolbox if you are designing a circuit. Okay? So those are all reasons that we care about op amps. Okay? So let's talk a little bit about how they work. Basically, an op amp is drawn like this. It's a little triangle, and a triangle is a generic symbol for an amplifier. Okay? So in this case, it's a triangle and it has 2 inputs and 1 output. The top input is called the inverting input. The bottom input is called the non-inverting input. Yes, the positive sign is the one that's non-inverting. The negative sign is the inverting input. Yeah. And then we have our output over here. In addition, op amps are connected to a power supply. So they have a positive supply voltage and a negative supply voltage. Okay? So since they draw power from this external power supply, we call these active components. That means that they draw power from an outside source. Most of the components that we've looked at so far do not do that, right? Resistors, capacitors, inductors, diodes, those are not connected to a power supply. So we call those components passive components. If they don't have an external power source, they're passive. If they do have an external power source, like this op amp, then we call them active components. Okay? So that's what's happening with the op amp. It's an active component. All op amps have a connection to a positive supply voltage and a negative supply voltage. But for the sake of making the drawing clearer, those connections are often not shown. Okay? We'll see in a minute that you have wires going from the output back to the inputs. So if you show the supply voltages as well, the drawing can get pretty cluttered. So oftentimes the supply voltages are not shown, even though they're always there. Okay? So the basic thing that an op amp does is that it amplifies signals, and the way that it does that is that it looks at these inputs and it draws electricity from the external power supply, and it uses that external power to amplify the input signals. Okay? So, like I said, there are 2 golden rules for analyzing op amp circuits. And if you can understand those, then you can analyze just about any circuit that's out there. So let's talk about those rules. So rule number one is that the input voltages are the same. So the voltage at the inverting input is the same as the voltage at the non-inverting input. Rule number two is that no current flows into either input. Okay? So that's all there is to it. If you can remember those two rules, or write them down where you can find them, then you can understand just about any op-amp circuit that's out there. Okay? So let's do an example and see how it actually works. So we're going to start with an inverting amplifier circuit. So an inverting amplifier circuit looks like this. Got our input here, resistor there. And then our output is over there. We call this resistor on the left the input resistor, or R in. This resistor on the top is the feedback resistor, or R feedback. Okay. So let's pick a specific example here. Let's say that we have a 1 kilo ohm resistor there, and we have a 7.5 kilo ohm resistor up there. And then let's say that we have an input voltage of 2 volts. And what I want to know is, what is the output voltage? Okay. So I say that if we know these two rules and we use them with this circuit, we can figure out what that output voltage is. Okay? So let's see how that works. Do we know what the voltage is at this point right there?
Yes.
Yeah? What is it?
0 volts.
0 volts, that's right. Because it's connected straight to ground. So we know that that's 0 volts. So do we know what the voltage is up there? What about rule number 1? That's right. Rule number 1 says that the voltage at the 2 input terminals is the same. So if we have 0 volts at one input terminal, we must have 0 volts at the other input terminal, right? You guys with me so far? Okay. All right. So now I want to know how much current is flowing through the input resistor there. Can we figure that out? Yeah? Yeah, I think so, because we know that we have a 1 kilo ohm resistor, and we know that the voltage drop across that resistor is 2 volts, right? We've got 2 volts on one side, 0 volts on the other, so we have a difference of 2 volts across that resistor. So what law do we use to figure out the current? Ohm's law, that's right. So we say Ohm's law is like this, V-I-R. So I equals V over R, so that is 2 volts over 1,000 ohms. So what does that come out to be?
2 milliamps.
2 milliamps, that's right. Whenever you have a 1 kilo ohm resistor, it makes the math really easy. That's why I like to use them. You just take however many volts you have across that resistor, and you get that many milliamps, right? So we have 2 volts across a 1,000 ohm resistor. That means that we have 2 milliamps flowing through it, okay? So we know that the left-hand side of this resistor is got a higher voltage than the right-hand side. So we've got 2 milliamps, and the current flows from high voltage to low voltage in the way that I analyze the circuits. So we know that the current is flowing that way, and it is 2 milliamps, okay? So now the next question is, how much of the current flows into the input terminal and how much of it flows to the feedback resistor? Say that again? That's right. That's right. Rule number 2 says that no current flows into the input terminal. So all of the current has to flow up this way through the feedback resistor. So we had 2 milliamps down here. We must have 2 milliamps up there, right? So now we've got another situation where we can use Ohm's law, right? We've got 2 milliamps flowing through a 7.5 kilo ohm resistor. So how much voltage do we have across that resistor? 15 volts. You can use Ohm's law and multiply it out, and you get 15 volts. Okay? So that means that the output, so we have 15 volts across this resistor up here. And we know that the left-hand side is more positive than the right-hand side because the current is flowing from left to right. So we have 0 volts right here, like we said, and then we go down by 15 volts. So what does the output voltage equal? 0 minus 15 is what? Right, minus 15, right? So we have minus 15 volts at the output. We had 2 volts coming in, we have minus 15 volts on the output. Okay? So we just used those 2 rules of op amps, and we were able to figure out what our output voltage is just using those 2 rules. Okay? Yeah?
Can you say why do you get negative 15?
Rather than positive 15?
Yeah.
Well, so we know that the current is flowing from left to right on this resistor because we have 2 volts over here and 0 volts there, so the current flows from higher voltage to low voltage. So it flows from left to right there. And then it has to keep flowing in the same direction. So it's flowing from left to right over here. And we know that we figured out that there was 15 volts across this resistor. The current is flowing from left to right. That means that the left side is more positive than the right-hand side. So we must be going down by 15 volts. So we're starting at 0 volts over here. We're going down by 15 volts. So that ends up with minus 15 volts at the output.
So the output with reference to ground would be negative.
Yes, yes. So we have positive 2 volts in here, 2 volts higher than ground, and we get out minus 15 volts, 15 volts lower than ground. Okay? That's why we call this an inverting amplifier, because it inverts the sign of the voltage. If you have a positive voltage going in, you get a negative voltage coming out. And negative voltage going in would give you a positive voltage out.
So you also said the voltage supply positive and negative voltage supply. So 15 will 15 volts exceed one of the rails?
Ah, so that's a very good point. So we said that this was an active component, right? Because it draws the power from the power supply. So that has a lot of advantages. It means that this amplifier can give you a lot of power, but it also comes with some drawbacks, like you alluded to. These power supplies, you have a positive supply voltage and a negative supply voltage, and they are limiting the output voltage that you can create. You cannot create an output voltage that's greater than your positive supply or less than your negative supply. Okay? So if you had a plus and minus 20 volt supply, then you could get the negative 15 volts out like we discussed on the board there. If you had a plus and minus 10 volt supply, then the op amp would not work properly with that particular setup that we had up there. It would try to give you minus 15 volts, but it would only be able to give you about minus 10, or whatever its lower supply limit was. Okay? So these voltages determine the maximum and minimum output that you can have from your chip. Okay? So if you are designing an op amp, you really need to think a lot about the signals that you're going to have and the amplification that you want in order to determine the positive and negative supply voltages that you're going to use. Okay? Because you can't get output voltages that are higher than those supplies. Okay? Any questions so far? Okay, so we used these two golden rules of the op amp to figure out what was going on in this circuit. And sure enough, they worked out. We were able to figure out our output voltage, but it took kind of a while, right? So it would be nice if there was a shortcut where we could figure out the output voltage more quickly. And it turns out there is. Okay? So if you did this a bunch of times, what you would see is that there's a formula you could use. You could figure out a formula. And the formula is that V out equals V in times R feedback divided by R in. We call this quantity in the parentheses the gain. Because that determines how much bigger the output is than the input. So let's work through that in this example and see if it if it holds true. Okay? So here the gain is 7.5 kilo ohms over 1 kilo ohm. So if we were to draw this out, we would say V in times 7.5 kilo ohms over 1 kilo ohm, and that just works out to be 7.5. Oh, I left out an important thing, which is the negative sign. Yeah, so this is V in times negative 7.5. Okay. So in this case, our input voltage was 2 volts. 2 times negative 7.5 comes out to be minus 15. So this works, yeah.
So your answer is always going to be negative?
No. So say I put in -1 volt. Then -1 times negative 7.5 would give you a positive 7.5 volts. So the inverting amplifier always inverts the sign. Okay. So any questions about that? Okay, so if you are using the inverting amplifier a lot, then you can use this formula, and that will allow you a quick way to figure out what the output voltage is and what the gain is. But if you can't remember the formula, you can always go back to the 2 golden rules, and they will allow you to analyze the circuit. Okay? All right, so that's how inverting amplifiers work. Now I want to spend a minute talking about how non-inverting amplifiers work. Okay? So non-inverting amplifiers look kind of similar to inverting amplifiers. Non-inverting amplifiers have an input resistor. They've got a feedback resistor. And so if you're not careful, you might think that you might just glance at them and think that they're the same. But there are some subtle differences, okay? In the case of a non-inverting amplifier, the input voltage is connected to the non-inverting terminal, right? With the inverting amplifier, the input goes to the inverting terminal. Non-inverting amplifier, input goes to the non-inverting terminal. Kind of make sense? All right, so the input goes to the non-inverting terminal. Here, our in is connected to ground over there. All right? So, and then our feedback is still up there. So, a subtle difference there, but it is important, and it does affect the way that the circuit works. Okay? So, so what we can do is that we can look at an example over here and figure out how this is going to work. Okay? So let's say that we have say we have 3 volts there, and then we have 5 kiloohms up here, and 1 kiloohm down there. Okay? So let's try and figure out what the output voltage is. Well, we know that we have 3 volts at the non-inverting terminal. So how much voltage do we have here at the inverting terminal? From rule 1? Yeah. 3 volts there as well, right? That's what rule number 1 says. The 2 voltages at the inputs are the same. So 3 volts over here gives us 3 volts over there. So now again we have an Ohm's law problem with this resistor. We have a 1 kiloohm resistor with 0 volts on one side and 3 volts on the other side. So how much current is flowing through this one? Use that sort of shortcut that I told you about over here. 3 milliamps, right? Now you see why I love those 1 kiloohm resistors so much. It makes the math really easy, right? So 3 milliamps flowing through there. And in this case, the current is going to be flowing from right to left, because the right side of this resistor has a higher voltage than the left side. The right side is at 3 volts, the left side is at 0. So current flows from right to left. Okay? What does rule number 2 say about how much current flows into the op amp? None, right? 0. So how much current has to be flowing through our feedback resistor? Well, we've got 3 milliamps coming down here. We know that we're not getting any of it from the op amp. So how much is coming from the other resistor? 3 milliamps. Exactly. Okay. So we've got 3 milliamps flowing that way. So that's 3 milliamps flowing across a 5 kilo ohm resistor. Right? So how much voltage do we have across this resistor? Use Ohm's law again. 15 volts. Okay, so we have a 15 volt difference across this resistor, and the current is flowing from right to left. It always flows from positive to negative, so that means that the right hand side has to be more positive than the left hand side. Okay? All right, so now we can analyze this circuit here and try and figure out what the output voltage is. So here we know that we have 3 volts at the inverting terminal, and then we go up by 15. So 3 plus 15, what does that equal? 18. So our output voltage is 18 volts. Okay? Any questions about that? Okay. So again, we use the 2 golden rules of op amps to figure out the output voltage of this circuit. And just like last time, there is a shortcut formula that we can use if we're looking at lots of non-inverting amplifiers. Here, we say that V out equals V in times R feedback over R in plus 1. Okay? So this quantity in the parentheses is the gain, again. But this gain is a little bit different than the last one, right? For one thing, this gain does not have the negative sign in it, right? That's why we call this a non-inverting amplifier. It does not invert the sign of the input voltage. So we had a positive voltage going in, we get a positive voltage coming out. Right? That's what we mean when we say it's non-inverting. So there's no negative sign in the gain, and also there's this plus 1 thing going on. Okay? So let's see how this works with this particular circuit. So in this case, V out is our input voltage, which is 3 volts times 5 kilo ohms over 1 kilo ohm plus 1. So that is 3 volts times 5 plus 1, which is 3 volts times 6, which equals 18 volts. So that's what we came up with, right? So you can use this formula to figure out the output voltage, or you could use the 2 golden rules of op amps to figure out the output. Okay? Either way, gives you the same answer. If you can remember this formula, it's a little bit quicker, but if you can't, you can always fall back on the 2 golden rules and you'll never go wrong, okay? So, any questions about that? Okay, so we talked a little bit about inverting amplifiers and non-inverting amplifiers. Now I want to go on and do a preview of today's lab. So, like I said earlier, we're going to skip the multi-sim in your lab book. So we're going to start on part 3A, and that's where we're going to build real circuits. So we're going to build an inverting amplifier, and then we're going to build a non-inverting amplifier. And I'm going to show you how we can do that. I'm going to pull down the screen and put up the projector and actually show you how to do that. Okay? I'm sorry, any questions before we go on and do the lab preview? Yes?
What about the negative and positive voltage supply?
Yeah, what about them?
So are those just like not a part of the like entire circuit, or are they are they just kind of like keeping it on, basically?
They are connected, they're always there. They're just not shown in the diagrams because the diagram would be pretty cluttered if you had the positive voltage supply and then you were trying to draw the feedback resistor on top of it. So those positive and negative supplies are always there, they're always connected, they're just not often shown in the circuit diagrams. Is that what you're asking?
Yeah.
Okay. And that brings up a good point, actually, because we haven't really used positive and negative supplies in our labs before. So far, we've always been using only a positive supply. So let's talk for a minute about how we could actually create a positive and negative voltage supply. Okay? For one thing, our power supply units themselves that sit on our desks don't really have anything that's labeled as a negative output, right? What they have is they have 2 separate power supplies that are adjustable. So you can set the voltages on each one of these to whatever you want, but they are separate. So this one's got a positive terminal and a negative terminal, and then this one over here has a positive and negative terminal of its own. Right? So we need to somehow take these 2 supplies and use them to make a positive and a negative supply. So what we're going to do is we're going to connect them together in series. So we connect the positive terminal of one supply to the negative terminal of the other supply. And then we call this middle point ground. Okay? So let's say that we had 12 volts up here and 12 volts down there. Well, we're calling this point in the middle ground, or 0 volts. And from 0 volts, we go up 12 volts over here. So that gives us a positive 12 volt output from one side of this supply, right? By the same token, down here, we start at 0 volts and then we go down by 12. So that means that this other output from this other supply is minus 12 volts relative to ground. Okay? So by connecting our 2 sources, our 2 power supplies together in series, we're able to create a positive and negative output voltage. Okay? So let's talk about what that actually looks like in practice. The power supplies have these little sockets that are on them where we connect our wires for the positive and negative voltages, right? So each supply has 3 little sockets. It's got a black one, a green one, and a red one. The red one is the positive, the black one is the negative, and then the green one is something called chassis ground. That means that it's hooked up to the chassis of the device, the outside shell of the power supply. So in order to connect these in series, we have to connect the positive terminal of one side to the negative terminal of the other one. So what we're going to do is we're going to take a wire and connect it from the positive terminal of one side over to the negative terminal of the other side. Then we said that that's also ground, so we're going to have this wire coming down where we can use it as ground in our circuit. Okay? So I know that this pen is just about dead, but it's the only green one I have. So we're going to imagine that this is going down, and that wire is ground. Okay? So you can all sort of imagine a green wire there. And then we're going to have a black wire over here connected to the negative. That's going to be our minus output voltage. And then we have another wire connected to the positive side of this supply, and that will be our positive output voltage. Okay? So we're going to be using wires that have 3 cables in them. So far, we've used power supply wires that only have a black and a red cable. Now, we're going to use power supply leads that have a black, a red, and a green lead all together. Okay? And you're going to hook them up to the power supply just the way it's shown on the board here. The black side goes to the black wire, the red side goes to the red wire, and then the green wire bridges between the red terminal on one side and the black terminal on the other. Okay. Everybody sees a green wire and wants to plug it into the green holes in the power supply. Don't do that. It's not going to work. Okay. It's not going to hurt anything, but your circuit's not going to work. All right. So connect it up just the way that I've shown it there on the board. There's also a diagram in your lab book that shows the same thing that hopefully can serve as a reminder. Okay.
Can you check those out?
You might have to check them out, or they might just put them in a pile at the back of the room. So one way or the other. All right. So let's talk about how we can actually construct this circuit. So your lab book has this helpful little diagram on the bottom left-hand side here that shows the op amp chip with a little triangle in the middle. And that should sort of help you visualize how to translate the triangular symbol that we draw on the board into this actual chip, right? The chip itself is this little black thing with 8 legs. Doesn't look very much like that triangle that we drew on the board, right? So this diagram should help to make the connection between the two. So pin number 2 on the chip corresponds to the inverting input on the op amp. Pin number 3 on the chip corresponds to the non-inverting input. Pin number 6 is the output. And then the power is connected between pin 7 for the positive supply and pin 4 for the negative supply. Okay? Yes, question?
Can you have like a chip that has more like triangles in it on this?
A picture that has more what?
No. Do you have a chip
Oh.
that has more triangles in it?
Yes, yes, it is possible, right? So this particular chip only has the single op amp in it, but you can buy other chips that have 4 or 8 op amps included. So, so those are available if you need to use more than one. Okay? Yeah.
Where's the ground
Ah,
connected? It's not shown.
right. It's not shown. And that's on purpose because the ground can be connected in different places. Remember with the inverting amplifier, the ground was connected to the positive or the non-inverting terminal. Whereas with the non-inverting amplifier, the ground was connected over here before the input resistor. So the ground can be connected in different places.
So the AC does not need a ground.
The AC,
Except
what?
for the circuitry inside the chip, it doesn't need a ground.
Right, right. The chip itself does not need a ground connected directly to it. Yes?
What do like pins 1, 5, and 8 do?
Right. Good question. Pins 1 and 5 are used for something called an offset null. That's something which is used for constructing very precise and delicate circuits. We are not going to be using that in this case. Okay. So if you had very high gain circuits that were dealing with very small or weak signals, then you could use that offset null. But we don't need to do that here. Pin 8 is not connected to anything. So they still included it on the chip because it would look funny if it only had 7 legs, but it's not doing anything. Okay. Other questions? Okay, so that's a little bit about the chip itself and how to set up the power supply. This is the circuit that we're going to build first. So here the input is going to the input voltage is going to the inverting input terminal. So what type of op amp is this? Or what type of circuit is it?
Inverting.
An inverting amplifier. Right? The input goes to the inverting terminal. It's an inverting amplifier. Okay? So we're going to build an inverting amplifier first. So let's talk about how we're actually going to do this. So the place to put your chip is in the middle of the board with one set of legs on one side of this channel and the other set of legs on the opposite side. Okay? It fits on there very nicely. That's exactly what this channel was designed for. So that's where you want to put it. Do not put it over here with all the legs on the same side of the channel, because that way pin 1 would be connected to pin 8, pin 2 would be connected to pin 7, and so on. And as we've seen in the circuits, we don't really want that. Okay? So put it right here in the middle with one set of legs on one side of the channel and the other set of legs on the other side. Okay? So we got our chip in place. Now we want to start hooking up some of these resistors. So we'll put the input, we'll put the feedback resistor there first. Now you'll notice that there are these little numbers at each of these points on the circuit. These numbers correspond to the pin number on the chip. So somebody was very helpful. They labeled the diagram for you so that you know which pins you have to use when you're making these connections. If they hadn't put those there, you would have to be flipping back and forth between your diagram here and your diagram over here to figure out which point was which. But since the pins are already labeled for you, you can just keep looking at this diagram the whole time. Okay, so this says that our feedback resistor is going to go from pin 6 over to pin number 2, right? So what we're going to do is we're going to have one side of our resistor in pin 6, the other side in pin 2. The way that the pins are numbered is that pin number 1 is the top left-hand corner of your chip. Okay? The top side is noted or marked with a little indentation or a small circle. Okay? You can't really see them on the screen up there, but there's a little indentation and a small circle on this side of the chip. So that's the top of the chip. So this is pin 1 up here. Our resistor goes from pin 2 to pin 6. So one side of the resistor is going to go there. The other side is going to go into pin 6. So if we count down on the left, we go 1, 2, 3, 4. Bottom left-hand side, bottom left-hand corner is pin 4. Then the numbering continues around in a horseshoe shape. So the bottom right-hand corner is pin 5, and then pin 6 is the right-hand side, second from the bottom. So that's where the other side of our resistor is going to go. So now we've got a resistor going from pin 2 to pin 6. That's our feedback resistor. We'll connect our input resistor here. One side is going into pin 2, the other side is going to be connected to our function generator. So we got that in place. Now we're going to start hooking up our ground and our function generator, okay, and our power supplies. So we can do the power supplies first. One power supply, the plus 12, is going to go to pin 7. The negative 12 is going to go to pin 4. Then the ground is going to go to pin 3. Okay? So I've got these little jumper wires in place. I can hook them up to my power supply leads. 7 is positive, 4 is negative, and for the inverting amplifier, 3 is ground. Okay, so I've got my power supply hooked up. Now the last thing I need is the output. So that is coming from pin 6. Just like the resistor is connected to pin 6. And our input is coming from our function generator, and that's going to be connected to this resistor over here. Okay, so I'll put one jumper wire in there, connect the red lead from our function generator to the input, and then the black lead from the function generator is going to be connected to ground. So that'll be connected there. Okay, so now we've got our circuit constructed. Now we need to measure the outputs from our circuit. Or we need to measure two things, really. We're going to measure the input and the output here. Okay? So the input signal is going to go, well, we're going to measure the input signal right where it's connected and then we're going to measure the output signal where it's coming out on pin 6. Okay? So we're going to use 2 leads from our oscilloscope to make our measurements. I like to measure the input signal on channel 1, so I will connect the oscilloscope there at our input, and then the small black clip from the oscilloscope gets connected to ground. And then I'm going to measure the output on channel 2 of the oscilloscope. So that'll be the second probe connected to pin 6. And again, the clip from that probe is going to connect to ground. Okay. So now I've got everything hooked up. I'm measuring the input and the output voltages. So let's take a look at what they look like on the screen. Okay. So, is there a question?
Yeah, where's the resistor on the left? Where's that connected to?
This resistor is the input resistor. So it's one side is connected to the function generator and the other side is connected to pin 2. Okay.
Okay.
Yeah.
The middle green wire, that's also connected to ground, right? Or is that?
Yes. Yeah, this green wire is the ground from our power supply. So we'll turn on the power supply. We'll set both of the voltages to 12 volts because this shows a plus and minus 12 volt supply for our op amp. And please remember to plug the positive supply into pin 12 and the negative supply into pin 4. If you get those reversed, the op amp will blow up, okay? It's not quite as spectacular as the capacitors, but it'll still pop pretty well, okay? So try and remember to get those supply voltages in the correct place. If you get them backwards and the op amp blows up, it's not the end of the world. We got more of them, but just try and get them in the right spot, okay? All right. Cool. So now let's take a look at what this looks like on our screen. So all right. Right now, the signals are very large on the screen. They're going off the top and bottom of the screen, so we can't really see what's happening very well. So what we have to do is we have to zoom out a little bit in order to see the tops and bottoms of the signal. Okay? So I'm going to zoom out in the vertical direction for that one, and zoom out in the vertical direction for that one also. Okay? Now, there's a couple of things to notice here. First of all, so the input signal is in yellow and the output signal is in blue. Does the input signal look like the output signal? No. The input signal is this nice sine wave, but the output has got these sort of bottom and top parts cut off. Okay? So, what do you think might be going on there? Well, remember how we talked about the power supply and how that limits the amount of voltage that you can get out? Well, our power supply is plus and minus 12 volts, right? So we're not going to get out more than plus or minus 12 volts. Ideally, the input would look exactly like the output. But here the output has got these bottom parts cut off because the bottom part here is about 2 divisions below 0. Each division is 5 volts, so you can see it goes down about 10 volts, maybe a little more, and then it gets cut off, right? Right around that minus 12 volt supply. Similarly, it goes up about a little over 10 volts, and then it gets cut off on the top side also. So this is called clipping. That's what happens when you try to create an output signal which is bigger than your power supply. Okay? So that's clipping. So the reason that we're clipping is that right now the input voltage is much bigger than it's supposed to be. In the lab book it says that our input voltage should be about 100 millivolts peak to peak. Who can tell me approximately how much voltage we're getting peak to peak up here? I heard 4, almost. Getting closer. So each division is 2 volts, right? So it would be 4 volts from the middle of the signal to the bottom of the signal.
8.
Right. 8 volts total from the top of the signal to the bottom of the signal. So we're getting about 8 volts in peak to peak. We want 100 millivolts. So we need a much, much smaller signal going in. So what I'm going to do is I'm going to dial the signal down. I'm going to turn the amplitude way down on my input. So now you can see that the output does look like a sine wave. Okay? So the input is a sine wave and the output is a sine wave. So this is more like what we are expecting. Okay? Now you'll notice that when the input signal goes up, the output signal goes down. We say that this is the input and the output signal are out of phase when this happens. If they both went up together and down together, then we would say that they were in phase. Okay? So they are out of phase because this is an inverting amplifier, right? When the input voltage is positive, the output voltage is negative, and vice versa. So this is what we expect to see. This is a characteristic of the inverting amplifier. Okay? Any questions about that so far? All right. So I've turned my input signal down, but I still think it's not quite small enough. Okay? I'm going to look at the measurement here, and we see that it's about 1.5 volts peak to peak. Okay? But my knob is all the way down. I've turned the knob as far to the left as it'll go, and it's still not low enough, right? It needs to be 100 millivolts. So what I'm going to do is I'm going to pull that knob out towards you, okay? And that makes the signal smaller. So now if I zoom in, I'm seeing that it's about 130 millivolts peak to peak. So we're getting closer, but we're still not there. So I'm going to do one more thing. I'm going to push a little button on the function generator that says ATT minus 20 dB. Okay? A lot of letters there. ATT stands for attenuation. That means it's making it smaller. And the minus 20 dB means that it's 10 times smaller. Okay? So now if we look at this signal, well, we actually zoomed in to the limit of the scope, so we can't see it any bigger on the screen than it is right here. But we can see that it's now a little bit too small. So now I can use the knob, turn that up a little bit, and get closer to that 100 millivolt peak to peak that I'm looking for. Okay? So again, it's pretty touchy. You just get it close. It doesn't have to be perfect. And you call it good. Okay? So now I'm getting the 100 millivolts peak to peak input that I'm expecting. here I'm using the 7.5 kilo ohm feedback resistor and the 1 kilo ohm input resistor, okay, with an inverting amplifier. So remember, the gain is feedback resistor divided by input resistor. So the gain would be 7.5 over 1, or 7.5, right? So the output should be 7.5 times bigger than the input. If I have an input voltage of 100 millivolts peak to peak, how much output voltage would I expect to get, approximately? So 7.5 times 100? Be about 750, wouldn't it? Yeah, so, okay, so if I zoom in on my output, well, that's bigger than I expected. Maybe I'm using the wrong value resistor. Well, I'll have to look into that a little bit. Maybe I picked the wrong value resistor here. But, I grabbed a 15 kilo ohm resistor rather than a 7.5. So that would be the problem. So with a 15 kilo ohm resistor, the output should be about 15 times bigger than the input. So I would expect something around 1.5 volts. I'm seeing 1.35, so it's, you know, it's in the neighborhood. Okay? So that's how we construct a circuit, and that's how we look at the input and output voltages. So we can actually calculate a gain or measure the gain using the oscilloscope. The measured gain is the output voltage divided by the input voltage. So in this case, it would be about 1.35 volts divided by 100 millivolts. So the measured gain here would be about 13.5. The calculated gain would be calculated using those functions that I showed you earlier. So the calculated gain would be 15 volts, or I'm sorry, 15. So you could calculate and measure the voltage and compare the gains that way. Okay. So that's what you're going to do in your lab book. You're going to build this circuit, and then you're going to draw what you see on the screen in your lab book. Okay. And then you're going to write down the gain. It'd be nice to write down the measured gain as well as the calculated gain. Okay? You're going to do that for the inverting amplifier and then also for the non-inverting amplifier. So you can construct a non-inverting amplifier and draw the picture from that in your lab book as well. So are the signals going to be in phase or out of phase for the non-inverting amplifier? In phase, exactly. When the input goes up, the output goes up, right? With the non-inverting amplifier. So they're in phase. So perfect. Any questions about that? Okay, then I will take roll and let you go.